Another theme that we've touched on, particularly with reference to the cyanobacteria and oxygen generation, but organisms and the environment co-evolve, as I mentioned earlier, and as I think will come up again as we talk about Mars. But is there a way of summarizing just how the atmosphere has shifted on a wide scale over the past billions of years on Earth? Like, what role do prokaryotes play in all of this beyond maybe just oxygen? What have the general shifts been?
Right. So the first thing to know is that the only source of oxygen on this planet that is sufficiently large to oxygenate the atmosphere and oceans is photosynthesis. And so the amount of photosynthesis that goes on depends on nutrient availability, which itself is related to physical processes on Earth. Um, and also, if I have a photosynthetic organism here that takes CO2 and water and makes organic matter and oxygen, and then I have a respiring heterotroph like you and me over here that takes organic matter and oxygen and respires it back to CO2 and water, that's a zero sum game. And so the way you break that zero sum is, again, through geologic processes where organic matter produced by photosynthesis, either directly or indirectly, gets buried in sediments. And then that creates the possibility that oxygen will increase in the environment. So what that tells us is that the process of photosynthesis, the nutrient availability that tells us how much photosynthesis is possible and who's doing it. A lot of that's coming from the biological side, but there's important components of the availability of nutrients, the burial of organic matter that come from the physical side. And when we put those together, the pattern, at least that's emerged, is that for the first 2 billion years of Earth history, there seems to be, at best, very low and transient oxygen in Earth's surface environments. Then about 2.4 to 2.2 billion years ago, there's a revolution. And now the atmosphere has some oxygen, the surface ocean does, although most of the deeper ocean remains oxygen free. And that certainly required cyanobacteria. It also happens at a time when continents are emerging above sea level, and so we have more weathering and erosion of nutrients into the ocean. So I think it probably represents an interplay of Earth and life. The amount of oxygen that accumulated actually wasn't that much, maybe 1 or a couple percent of today's levels. And that may have fluctuated a bit through time, but it doesn't start going up permanently until, around 600 million years ago, and that's when chemical signatures tell us oxygen is starting to go up. We see a fundamental change in Earth's phosphorus cycle at that point, which means there's more nutrients becoming available. We have evidence of that oxygen is going up, and that's on the timescale we start to see macroscopic animals, which need relatively high oxygen concentrations to function. And again, that still didn't bring us to modern levels, probably something like 10 or 15% of today's levels. But then by about 400 million years or so ago, during the Paleozoic era, so-called, we have evidence that oxygen is going up to essentially modern levels. And as I said, I think earlier, that coincides with the evolution of land plants, which have some decay-resistant tissues that accumulate in sediments, giving us coal and things like that. So on the long run, then it looks like you can divide Earth history into kind of 3 chapters: no oxygen, a little oxygen, and a lot of oxygen. And the boundaries between those 3 chapters do seem to represent places where, in various ways, the physical and biological Earth are starting to interact in new ways.
That gets us to exactly where I wanted to go. We've skipped a lot to reach the present, but with the exception maybe of some of the experimental research programs we've talked about with regard to figuring out the early processes that, or the processes that led to early life, and perhaps their relationship to synthetic biology. Most of our conversation has been backward looking, and backward looking at that. But granted that your expertise in what's happened over the past billions of years of life, how does it equip you to think about what's going on in Earth's life and atmosphere today that other biologists or zoologists might not be attuned to? And I know that this is a huge subject that we don't have time to get into all the nitty gritty of, but I just like a general idea.
Yeah, well, I'd be hesitant to say that other biologists aren't attuned to this, but I do think that aspects of the past do provide a distant mirror that helps us to understand what the rest of the 21st century and beyond may be like. Some years ago, um, I got interested in what is the largest known mass extinction at the end of the Permian period, 252 million years ago. And I just started thinking about what might cause this. And I was very taken by the fact that geologists had done a very good job of documenting the facts of the extinction and some of the environmental changes, but not a very good job of relating that to who died and who survived. And it struck me that that was a little bit like going to a murder scene and not looking at the victim. Um, and so what I did was it struck me that some of the physical processes going on might have produced a lot of carbon dioxide. And we now know, we didn't at the time, but we now know that this is the time when some of the largest volcanism that we know of in the history of the planet took place. And it would have spewed immense amounts of CO2 into the atmosphere on a fairly short time scale. So what I did with my buddy Dick Bombach was literally, we went to the library for 3 months and just read the experimental literature on how do organisms respond when you subject them to high CO2 levels. And it turns out some respond very poorly, some can actually compensate for it. And it turns out that when you divide the living biota up into the things that are vulnerable and perhaps more tolerant of, increased CO2, that does an excellent job of actually predicting what did and did not go extinct at the end of the Permian period. And so I think that was probably the first time anyone ever said rapid increase in CO2 could be very bad for the biota. Well, fast forward to the 21st century, and we are now increasing the amount of carbon dioxide in the atmosphere at a geologically very rapid rate. We are seeing the effects of this on the biota, which are very similar in many ways to the effects that we see recorded at the time of the Permian extinction. And it's led to some, in my case, some, very happy collaborations that I recently co-authored a paper with a group in Germany who are probably the leading lab looking at the physiological response to elevated CO2 among marine animals. And I think it shows that, the past does have something to tell us about the future. It certainly is consistent with everything we're observing today, and it suggests that unless we are smart enough to change our ways, that we will move toward, well, we are moving and have already moved significantly toward a warmer Earth. That is going to have consequences for different types of plant and animal. And importantly, it will have consequences for humans as the capacity of different areas for agriculture will change, water availability will change. So we're heading into an unknown future, but in some ways, what the past tells us is that we should think very hard about how we collectively can respond to what we have done industrially, and all of us contribute to it, but how we can try to rein in global change in a way that will, vouchsafe happy, habitable environments for our grandchildren.